Welcome to the session 5 of our unit 1 of the financial modeling course. The session 5 deals with the financial distributions, efficient market hypothesis, and also predictability. By the end of this session, you should be able to test normality or otherwise of financial time series. You should be able to identify techniques used in testing the weak form efficiency. You should be able to conduct an empirical test to validate the weak form efficiency of the financial market. Financial distribution. An important assumption underlying many theoretical and empirical models in finance is that return series are mostly normal or normally distributed. This assumption is widely used in portfolio allocation model, in value at risk calculation, in pricing option, and in many other applications. But as we have earlier seen, we clearly saw from our earlier slides or our earlier sessions that the return series are mostly not normal, which is one of the stylized facts of the return series. Proving that return distribution are non-normal in research papers are mostly trivial. They are mostly not all that pertinent or relevant. Modeling market returns involves selecting the appropriate statistical distribution that describe the entire behavior of the data set. But we should also understand that most models in finance has this simplifying assumption that the return series is also independent and identically distributed or normally distributed, with a constant variance or a variance equal to unity. This description is only halfway correct. It is not always the case that the return series will be normally distributed. There are times that we see that some return series are, when we plot them, we see that they are either skewed to the left, indicating that they are mostly the data set subscribe or submit to negative news in the market more than it does positive news, and there are times that we see the data or return series when plotted also is positively skewed. So we can't be right or fully right when we say or when we assume that the return series are normally distributed. So to capture this stylized fact of normality, there is a need for us to capture the return series, that the data on the returns in their entirety. So we cannot consider some portion of the data set and then use that to make inference or make our supposition, or we cannot make an informed decision with a return series or with an estimation which was used or in which we only used a portion of the data set. So for instance, the VAR, which is the value at risk, and the expected shortfall, which is the ES, require capturing the risk properties of a return using only the quantile values in the left tail of the distribution, which represent losses or negativity. And so in our calculation of value at risk, here the emphasis is mostly on losses. So when we plot return series, the losses are mostly seen on the left side. So the center will be 0, and the right will be the positive returns, and the left will be the negative return, which is the losses. So the gains will be on your right, and the losses will be on your left. What we are saying is that in the calculation of value at risk, just as the name sounds, we are focusing on the risk element or the losses. So we tend to weight the loss, we tend to focus on the loss, and also in modeling for value at risk, we focus on the losses. The losses are of interest because assuming we are certain that we are going to make returns, or assuming knowing very well that returns are the reward for investment, then what we should be scared of is how possible it is for us to lose some of these returns. So table 1.8 depicts a summary statistics from the Ghana Stock Exchange All Share Index. The result indicate the lack of normality in the data set. The result indicate that the data is skewed to the right with a ketosis value above normal. So the ketosis has to do with the heaviness of the tail, so as to how uneven the data set is distributed. So even the ketosis and the skewness can tell you that the data set is not normal. So the above result is further showed in table figure 1.6 and 1.7, which is mostly a histogram and also a KQ normal plot. So as we earlier said, this is the histogram. You could clearly see from this plot that this data set is not equally distributed or normally distributed. This is the zero line that I was earlier speaking on, and this is the positive return. So all this portion has to do with positive return, and this portion is the negative return. So here we are talking about the impact of negative news in the market or the losses. So here, for the value at risk, we are saying that the focus will be on this portion. Here has to do with losses. So you could see that this is the center. Without even any means of computation, you clearly see that this data set is not normal, because we have a portion from here all the way to here which can never be equal, even graphically cannot be equal with the left side, indicating that the data set is skewed. This data set is skewed, so this data is not normal, because by normality we are saying that half of this portion, like this plot, this portion should be a mirror image of this portion, so they should be equally distributed. So if we are dividing a loaf, for instance, into two, and we said that it is equal, or the division is equitable, or we are considering equity in it, what we are saying is that half of the loaf should be given, or should be equal to the other half. So there shouldn't be a case where, for instance, in this plot, we should see that the half, let's say the right portion, the data, like the gains, let's say the gains are mostly higher, in this case are mostly higher than the losses, even though there were some series of losses, because from this plot you could see that this is the zero line, and so all this portion has to do with the positive and this has to do with negative, indicating that this is not a normal data set. And also the results from the summary statistics indicate that we had 741 observations, and the arithmetic mean, which is this mean, the center, the mean has simply has to do with the average return. So out of the 741 observation, the average mean, or the average returns, was 0.000143, which is quite insignificant, and we had a standard deviation of 0.00809. What we could also see is that the standard deviation, which is a measure of risk, is higher than the average returns, indicating that in this market there's the likelihood of we having more risk, or there is a higher risk in this market. And the ketosis and the skewness value also indicate that this data set is positively skewed, as we earlier said. So it is skewed to the right. The data set is skewed to the right. If this figure tends to be negative, then we will say it is skewed to the left. So as we earlier said, this data is skewed to the right. And the ketosis, which has to do with the tailness, is saying that there are heavy tails, and here we have excess ketosis, or what we call the leptoketic. So we said this data set is leptoketic, indicating that they are not uniformly distributed, and we cannot speak of normality for this data set. And the latter part, which is figure 1.7, is the quantile plot, which has to do with normality. This red line here is simply saying that if we are to have all our data set on these lines, or very close to this line, then there is a chance that our data set will be normal. But given that some of these data sets are found on this extreme, so here we are looking at the upper quantile, and at this point we are looking at the positive figure. So we are looking at the extremes at the positive side. These are the extremes at the negative, and this is similar to this portion. So here is similar to this portion, this negative portion, and this portion, or this higher quantile, is also similar to this positive portion in the histogram. All what we are saying is that if this data set is normal, then we should find all these blue points which has to do with the individual data set on the red line, which is a normal line, which is for normal data set. Now we are going to discuss the efficient market hypothesis and also the predictability. According to the efficient market hypothesis, all available information concerning the value of a risky asset is factored into the current price of the asset. Here, what we are simply saying is that to say a market is efficient, we are simply saying that that market cannot be predicted. An individual investor cannot predict this market, let's say using historical data or his or her own accurate forecasting or means of forecasting. So by efficient market hypothesis, we are saying that you can't use the previous day's price to predict subsequent prices, because the market is efficient, and we are saying that there is no way you can predict the prices. So even though you can choose to predict, but what we are saying is that it will not be accurate, because the market price of yesterday has nothing to do with the market price for today. So in essence, we are saying that the market or the price series are not correlated, or they are not, there are no serial correlation in the price series. So autocorrelation measures the strength of movement in the current return on an asset, RT, which returns on the same asset K periods. So by autocorrelation, we are saying that the price of, let's say, an asset yesterday will have an impact or will influence the price of the same asset today. So like in that order. So we are saying that the price today depends on the price yesterday, and the price yesterday will depends on the previous price before yesterday. So that's what we deal with. What is the meaning of autocorrelation? So for any series of returns, the autocorrelation coefficient for K lags is defined as we see in equation 1.10. So where the PT has to do with the price series, or it could even be the return series, and the RT has to do with the returns. So here we are computing the autocorrelation using this complex or this sophisticated mathematical equation. So according to the efficient market hypothesis, or by the efficient market hypothesis, all these applies. So if the series of returns does not exhibit autocorrelation, then there is no apparent pattern in their behavior. So we are saying the market is efficient. So positive autocorrelation shows that successive values of returns tends to have the same sign, and this pattern can be exploited in predicting the future behavior of returns. So when there is positive autocorrelation, or when there is autocorrelation, or when a data set is autocorrelated, what we are simply saying is that you can predict the successive values using the previous values, because there is some connection between the previous and the current. Negative autocorrelation, on the other hand, indicates an alternating sign, which is when you compute the mathematical equation that we saw in the other slide, in the previous slide, and we end up getting a negative autocorrelation. What we are simply saying is that if we are to predict the market using the negative sign, or the result from our autocorrelation, or the computation of our autocorrelation, then we are saying that if today it happens to, if the returns, or let's say the return series for today was positive, then the chances are that of the successive day or the next day will be negative. So means we have an alternative signs in the prediction. So if you predicted for a gain today, then tomorrow you should know that because the autocorrelation results gave you a negative, or was negative, it shows that there will be a negative chance tomorrow. So that's what this one also means. Autocorrelation in an asset is also the cornerstone of the whole idea of the efficient market hypothesis, because for a market to be efficient, we are saying that all the price of a risky asset is embedded or is inculcated in that particular asset or the price. So there is no way you can predict next day's price using today's price. So that's the whole idea of the efficient market hypothesis. So according to stock market price or returns, we are saying that the return or the price series are random. They are not predictable. So you can't predict them. That's what the efficient market hypothesis is trying to say. So either the stock price or the exchange rate market or any other financial market, when we say the market is efficient, we are simply saying that you cannot predict the prices or the return series. You can't predict them. So they are random. The price or the returns are random. So today's price cannot be predicted using yesterday's price, and tomorrow's price cannot be predicted using today's price. So an empirical test of the efficient market hypothesis with respect to asset market, it simply has to do with the test of autocorrelation. So for us to be convinced that the market is efficient, then after calculating our autocorrelation using our analytical tools like the eViews, what we are expecting is that the results should be zero, indicating that there are no correlation or there are no autocorrelation in the data set. Figure 1.7 and figure 1.8 here are simply return series. Figure 1.7 has to do with the return series on the Johannesburg Stock Exchange, which is South Africa, and the data set start from 2003 to 2015. We could see that, as we earlier saw in figure 4, these are return series. They are not price series, because the price series has this form of upward and downward trend, but here there is the idea of stationarity. So we could see this volatility clustering. Here there are clusters or volatility clusters in this data set. This is the. So what we are saying is that here, by the look of, we are saying that because the pattern in these return series are not constant, you cannot predict them. But we cannot just make this submission or this judgment by just looking at the price series, but sometimes, given the nature of the upward and downward trend. But with respect to figure 1, we could see that even though it is difficult to predict, but we could also see that there are some form of volatility clustering. So we could see that at this point there was, like, if assuming this is day 1, then we are saying that the day 2 is also dependent on day 1, because there is some form of connection. So here, this price series, even though it is hard to say, but we can see some form of autocorrelation in this price series, because it's like the price series are connected in a way. Sorry, the return series are connected in a way. So we could see that even as the returns were computed from the price, we could see that even with the price, you can't say all the information concerning that price or the price of the asset is embedded or is tagged in the price of the asset. But here, figure 1.8 depicts a randomly generated data set, which is 0 and 1. Here you could see that, unlike this place where there is some form of volatility clustering, you could see some connection with this plot, which figure 1.8, it seems this connection seems to disappear, because if you are to predict, the pattern of prediction will not be certain, given that there are different patterns, and you are likely going to have an inaccurate prediction if you have to predict this price series. So here we're saying these figures are randomly generated, and there are no, like, they are randomly generated, and there are no connection in this return series. So we should also understand that the graphical depiction in figure 1.7 and 1.8, as we saw earlier, cannot be the best or cannot be always accurate. We cannot be accurate in using the graphical representation. So there is an autocorrelation plot function. or function plot, where we try to plot the dataset and see whether they are autocorrelated. You could see that there are bricks here, there are bricks, and there are vertical lines. There are bricks. These are the break points. So these are the break points. So what we see is that the vertical lines tells us whether the datasets are autocorrelated or not. If the vertical lines, these lines, if they are found outside these boundaries, the bricks are the limitation or the limit. It measures the limitation, the limit, or the boundaries, or the boundaries beyond which the dataset cannot be found. So if the datasets are found outside these boundaries, then we are saying there are autocorrelation in the dataset. But in this figure, in figure 1.9, we could clearly see that this dataset is autocorrelated, given that these bricks are just here and here, but these vertical lines are wide, or they are set apart, and even these ones are outside these bricks or these boundaries, indicating that they are not random, and that there is the presence of autocorrelation in the data set. The same thing can be said of figure 1. This figure, the figure 1.1. Here too, we could see that these vertical lines are outside the boundaries. The boundaries are the dashed lines. Let me say the dashed lines. So this dashed line, there are two. If the datasets are found between these dashed lines, then we say there is no autocorrelation. But in our case, there is, because all these vertical lines, these ones, they are found outside the boundary of. So they are found outside the boundaries, which indicate that they are autocorrelated. In this session, we have discussed financial distributions, efficient market hypothesis and predictability, and the autocorrelation and partial autocorrelation. Thank you.